A 2.5 kilogram bicycle wheel with a radius of 0.35 meters turns at a constant angular speed of 20 radians per second. When a 0.3 kilogram reflector is at a distance of 0.12 meters from the axle. What is the angular speed of the wheel when the reflector slides to a distance of 0.28 meters from the axle? All right, so we talked about angular momentum, and we know that it is conserved, and that as the moment of inertia increases, therefore the angular speed or velocity will need to decrease. Okay, so in this problem, when the reflector slides outward, we have to think what's going to happen to our moment of inertia. And hopefully you recall from previous lessons that as the mass moves away from the point of rotation, we have a greater moment of inertia. So since there's a greater moment of inertia, that should mean our angular momentum is going to decrease. Or it should mean our angular velocity will decrease so that our angular momentum can be conserved. Okay, so we're going to use conservation of angular momentum, which means we need two pictures, a before and an after. So beforehand we have the reflector. It's not the whole way to the end. It's at 0.212 meters from the axle. Okay, and then later it's at 0.28 meters, so it's further out. Okay, so moving the reflector further out. Okay, let's go ahead and write down our givens now that we have our picture. Well, in the picture we have two objects. We have the wheel and we have the reflector. And if we look up here at the problem, we have the mass of the wheel, and that is 2.5 kilograms. And then we have the radius of the wheel, and that is 35 centimeters or 0.35 meters. And then we also have the reflector. Okay, so the mass of the reflector is given to us as 0.3 kilograms. And the radius of the reflector in the beginning is 0.12 meters. Okay? And then we have our after. Well, the mass of the wheel does not change, so it's still 2.5 kilograms. The radius of the wheel does not change. It is still 35 centimeters. The mass of the reflector is not going to change. It's going to still be 0.3 of a kilogram. However, the radius of the reflector is what changes. As the tire begins to spin, the reflector goes from somewhat close to a little further away. Okay? And it goes all the way out to 0.28 meters away. Okay? Now, we know that momentum is conserved. So that means that the angular momentum before is equal to the angular momentum after. Okay? We also know that momentum is equal to the moment of inertia times the angular velocity. Well, the before is going to use the initial angular velocity, and we are given that. The initial angular velocity, since they're spinning together, will be the same, and that is 20 radians per second. And afterwards, we're trying to find that. So we're trying to find our final angular velocity. All right, so now what do we need? Well, we've got omega I. We're trying to find omega F, so we aren't going to have that right away, but we do need to know these moment of inertia. Okay, so let's find the moment of inertia for the wheel. Well, the wheel is in the shape of a hoop. So if we look at our equations for moment of inertia, for a hoop, it is the mass times the radius squared. So let's go ahead and substitute in. The moment of inertia for the wheel is 2.5 times 35 hundredths squared. The moment of inertia for the wheel is 0.30625 kilograms times meters squared. Then we can find the moment of inertia for the reflector. The reflector is like a point mass traveling around. Okay? So if we look up the moment of inertia for a point mass, it is the mass times the radius squared as well. So it's the same equation in this case. So the moment of inertia for the reflector is 0.3 times 0.12 squared. And in this case, that is going to be 0.00432 kilograms times meters squared. Okay, so now in the before, we've got some moment of inertia, we've got the angular speed. So we want to find, we need to take the total moment of inertia times the initial angular speed. Well, the total moment of inertia is the moment of inertia of the wheel plus the moment of inertia of the reflector. And now we can go ahead, we actually have everything, so on the left side of our equation we can go ahead and substitute in right now. So we've got 0.30625 plus 0.00432 times 20. If we simplify that, we're going to get 6.2114. All right, so now let's look at the after side. In the after side, we've got to find our moment of inertia for the wheel. Well, nothing changed. The mass is still the same, the radius is still the same, so the moment of inertia for the wheel is still the same. It's 0.30625. However, the reflector did change, okay? It changed the radius, so that's going to change the moment of inertia, so we need to find that again. So 0.3 times 0.28 squared. In this case, the moment of inertia for the reflector is going to be 0.02352 kilograms times meters squared. Okay, so the moment of inertia for the reflector does change. All right, let's go ahead and substitute in and see what we find. So afterwards, we need to take the moment of inertia times the angular velocity at the end. So the moment of inertia is the total moment of inertia. Again, it's the moment of inertia of the wheel plus the moment of inertia for the reflector times the final angular velocity. Substitute in. Moment of inertia for the wheel, still 0.30625, plus the moment of inertia for the reflector, which changed to 0.02352, times the final angular velocity. Add those two together, we get 0.32977 times the final angular velocity. Divide both sides by 0.32977. We find the final angular velocity is 18 84 radians per second. We anticipated that this would get smaller, it'd be smaller than the initial, and it is, okay? Because the moment of inertia increased, the angular velocity needed to decrease so that we could have the momentum before be conserved and be the same as the momentum after.